Where are all the aliens? This is a question that has perplexed scientists for years. Since at least the time of the Greek philosophers, humans have speculated about the existence of other worlds. Today we know our night sky is literally teeming with exoplanets, planets that orbit the stars outside our solar system. And it was with great excitement that the world greeted the announcement on August the 24th in 2016 that scientists had detected a planet orbiting not just any star, but the star nearest to our own sun, Proxima Centauri. The discovery was particularly exciting because of the possibility that the planet, known as Proxima Centauri b, might have the conditions necessary to support life. So, is Proxima b another Earth? This puzzle has caused a stir in the scientific community for a long time. But recently, James Webb Space Telescope, or JWST, has just announced the clearest image of Proxima b in history, revealing an astonishing discovery that could change everything we know about the universe and life on Earth. Join us today as we dig deep into the mysteries of Proxima b and discover whether it could be the next Earth. The James Webb Telescope is well known as the largest telescope in space. Launched on Christmas Day in 2021, it is the perfect tool for investigating the secrets of distant worlds, paving the way for studying Earth-like planets. One of Webb's biggest advantages is the type of light it collects. Light comes in a lot of different varieties. The human eye can only see a narrow band known as visible light, but the universe contains lots and lots of light outside this range, including the higher frequency, higher energy forms, ultraviolet, gamma rays. Then there's the lower energy light with longer wavelengths, infrared, microwaves, radio. The Hubble Space Telescope collected visible light, ultraviolet, and a little bit of infrared. The James Webb Telescope is primarily an infrared telescope, so it sees light that's in a longer wavelength than what our eyes can see. This seems nerdy and technical, but it's actually what allows Webb to look further back in time than Hubble. Infrared light is often very old light due to the phenomenon called redshifting. When a light source is moving away from a viewer, it gets stretched out, morphing into a longer and longer wavelength, growing redder. The opposite is true as well. As a light source grows closer, the wavelengths shorten, growing bluer. It's similar to what happens when a siren goes by. The pitch increases as the siren approaches, then decreases as it trails away. Because space is constantly expanding, the farthest things away from us in the universe are moving away from us. And as light travels through space from those distant galaxies, the light is literally stretched by the expansion of space, said Amber Strawn, an astrophysicist at NASA who works on the Webb. Imagine a star that's really far away. The light from that star may start off in the visible spectrum, but it gets stretched on its journey to us. It grows redder and redder. So when we see distant galaxies with Hubble, they're sort of these little tiny red nuggets, Strawn says. Eventually these very distant, very old galaxies grow so red that they drop into the infrared spectrum. Webb can see this ancient light that has become invisible to the human eye. Conveniently, infrared light has other uses as well. It's a really good type of light to use to look at exoplanets. For instance, if you were on a planet that orbits another star and wanted to see Earth, visible light wouldn't be your best bet. The Earth peaks in the infrared, says Johns Hopkins Applied Physics Laboratory astronomer Kevin Stevenson, who plans to use the Webb in his research. So, if we want to be able to study an Earth-like planet in another solar system, what we really want to do is observe at infrared wavelengths because that's where the light from the Earth is being emitted, he said. Exoplanet scientists like Stevenson are going to use the Webb to analyze the atmospheres of these worlds. The Webb is capable of determining some of the chemicals in their atmospheres. We can detect water, carbon monoxide, carbon dioxide, methane, Stevenson said. While those aren't definitive signs of life on their own, they could begin to ask fascinating questions. What created that methane and carbon dioxide? And could it have been life? We all want to find another Earth, don't we? The prospect of answering the question, "Are we alone?" has been something that we've been asking ourselves for centuries. And I think with James Webb, this will provide us the first opportunity to really answer that question, Stevenson said. The Webb telescope is so powerful that it can actually see and image exoplanets rather than infer their existence like almost every other telescope has done before. It still isn't good enough to get a detailed picture, but JWST can see the light reflected off of an exoplanet's surface. That's why, long before JWST was operational, Avi Loeb calculated how JWST could use this ability to see alien cities. He based his calculations on the nearest Earth-like exoplanet, Proxima b. For many alien hunters, Proxima b is the prime candidate in the hunt for signs of intelligent alien life outside the solar system. The planet is 1.27 times the size of Earth, sits within the habitable zone of its star, so may have liquid water on the surface, and is just 4.2 light-years away, which, in interstellar terms, that is practically on our doorstep. However, as the star is relatively small, this habitable zone is close to the star, meaning the planet is tidally locked, with one side always facing the star. There is also speculation that it is very unlikely life could develop on the day side due to a constant stream of intense radiation from its host star. Proxima b is orbiting just 4.5 million miles out, or about 1/10 the distance Mercury is from the Sun at its closest point. Radio signals have already been detected from the area around Proxima b. However, radio astronomers believe this was likely just interference from natural sources. It is the tidal locking that prompted Professor Loeb to consider the possibility that LED lights might be detectable from Earth with the powerful James Webb telescope. By taking images of the exoplanet at multiple points of orbit, we can see both the day and night sides. We can then compare how bright and dim we expect it to be. And if there is a discrepancy, it should be due to artificial light from an alien civilization. But how sensitive will this technique be? Well, it turns out that if the night side has enough urbanization to emit 5% of the brightness of the exoplanet's day side, JWST could identify it. For some comparison, our bright city lights only illuminate the night side of the Earth by 0.01% compared to our day side brightness. But due to a quirk of how modern telescopes work, designed for spectroscopy, if these city lights on Proxima b were 1,000 times more narrowband than the star, meaning the range of wavelengths of light from the city lights is 1,000 times smaller than the star, the JWST could identify only 0.01% illumination. But JWST turned out to be much better than we anticipated. Webb's mirrors collected light from the sky and direct it to the science instruments. The instruments filter the light, or spectroscopically disperse it, before finally focusing it onto the detectors. Each instrument has its own detectors. The detectors are where photons are absorbed and ultimately converted into the electronic voltages that we can measure. Webb needs extraordinarily sensitive detectors to record the feeble light from faraway galaxies, stars, and planets. It needs large area arrays of detectors to efficiently study and survey the sky. Webb has extended the state-of-the-art for infrared detectors by producing arrays that are lower noise, larger format, and longer lasting than their predecessors. Webb uses two different types of detectors: a mercury-cadmium telluride detector, or abbreviated HGCDTE, or H2RG as it's known, for the 0.06 to 5 micron near-infrared measurements, and secondly, arsenic-doped silicone detectors, abbreviated SIAS, for the 5 to 28 micron mid-infrared units. The near-infrared detectors were made by the Teledyne Imaging Sensors in California, and H2RG is the name of the Teledyne product line. The mid-infrared detectors were made by Raytheon Vision Systems, which is also in California. Each Webb H2RG detector has about 4 million pixels, whereas the mid-infrared detectors have about 1 million pixels each. HGCDTE, or mercury-cadmium telluride, is a very interesting material. By varying the ratio of mercury to cadmium, it is possible to tune the material to sense longer or shorter wavelength light. Webb takes advantage of this by using two compositions of mercury-cadmium telluride, one with proportionally less mercury for 0.06 to 2.5 microns, and another with more for 0.6 to 5 microns. This has a number of advantages, including the possibility of tailoring each near-infrared camera, or NIRCam detector, for peak performance over the specific wavelengths for which it will be used. So, although the search for city lights on habitable planets may sound speculative, it is worth pursuing as a potential technosignature with planned instruments. What's more, these figures are now likely to be underestimated, and it is possible James Webb will detect far less illumination or see the same on much more distant exoplanets. Proxima b orbits its star every 11.2 days, providing 32.6 more opportunities for its possible inhabitants to celebrate their birthdays than we have on Earth, once per 365.2 days. The high demand for bright lights during birthday parties on the night side of Proxima b would be a reason for us to celebrate as well, if the signal were noticed by future telescopes. Once signs of life are found, sending a probe on Proxima is needed. But of course, a lot of technical challenges need to be overcome before we can hope to mount such a mission. In addition, a lot of questions need to be answered. For example, what kind of ship would we send to Proxima b or other nearby exoplanets? How long would it take for us to travel to it? The vast distance that separates us from Proxima b is terrifying. Compared to other regions of the cosmos, Proxima is almost in our backyard, but it would take approximately 78,000 years to go there with present technology, a calculation based on the maximum speed attained by our fastest probe, New Horizons, which was 59,000 kilometers per hour. If we wanted to reach Proxima in a reasonable 20 years, a spacecraft would have to travel at an average speed of more than 300 million kilometers per hour, which is about 28% of the speed of light. Regardless of this challenge, humans always seem to strive to one day reach out and touch the stars. And it appears that even NASA has decided to visit there before the end of this century, with a project that is facing stiff opposition in some scientific circles, but which the American Space Agency believes it can launch by 2069. A date, by the way, which is definitely not coincidental, as it recalls an event that occurred exactly 100 years earlier. That would certainly be a thrilling feat. To fulfill this dream, NASA will need a speedier method and more efficient technology to reach at least the nearest stars. Reaching Alpha Centauri system in an acceptable amount of time would necessitate the development of a propulsion technology capable of at least 10% of the speed of light. The greatest challenge is storing the sufficient fuel load to enable the spaceship to accelerate steadily to the desired speed threshold. In spite of the seemingly insurmountable obstacles, numerous interplanetary spacecraft designs have been presented during the past few decades. In the 1960s, research and tests were done in the United States as part of the Orion project. The basic concept was to use the shock wave produced by the consecutive detonation of numerous tiny nuclear bombs to propel a spacecraft at high speed. Someone understood the project's potential for interstellar travel as well. Originally, the project was intended to transport massive masses into orbit or permit human journeys to Mars, but someone recognized its potential for interstellar travel. In the initial design, the Orion intended to rapidly release nuclear fission bombs, which, when detonated directly behind the vehicle, would give it a large boost via the impact of the shock wave formed on a unique shield capable of absorbing the shock without harm. Nevertheless, this notion, which would alleviate a number of the aforementioned issues, remains speculative and may be used to launch small probes to the stars. During the same period of time, American physicist Robert Bussard presented an innovative solution to the mass problem by omitting the need for propellant. Thus was created the concept of the interstellar ramjet, a vehicle capable of gathering the hydrogen present between the stars and utilizing it to power a nuclear fusion engine. The collection of interstellar hydrogen would not be so simple, in addition to the challenges posed by the construction of the engine. In fact, assuming an average density of 1 atom per cubic centimeter to gather 1 kilogram of hydrogen at 1/10 the speed of light would require a funnel with a mouth of 5,000 kilometers in diameter, and the collected stuff would still be minimal in comparison to the requirements for propulsion. Interstellar ramjets, in all of its proposed forms, are therefore not regarded physically possible. In the 1970s, the British Interplanetary Society, led by British aerospace engineer Alan Bond, did a comprehensive study of the Daedalus variant of the Orion concept, possibly the most realistic interstellar ship design ever envisioned. Instead of nuclear weapons, the Daedalus was designed to utilize a succession of micro-explosions generated by the nuclear fusion of miniature deuterium and helium-3 tablets. The two-stage, fully autonomous spaceship may have reached 0.1 constant, or 10% of the speed of light, with a launch mass of 50,000 tons, or 93% of which was propellant. This would have allowed it to reach Proxima in slightly more than 30 years, then broadcast the data obtained during the flyback back to Earth. Another intriguing suggestion is the Star-Wisp laser sails, which overcome the issue of mass and heat by removing the motor and replacing it with the pressure exerted by a beam of radiation directed onto an extremely light sail. However, very innovative solutions are required to handle the issues of energy consumption and journey time. Since its conception in the first half of the 1980s, the interstellar sail concept has undergone a number of revisions and enhancements, mostly to reduce the energy requirements of the journey and make its operation more realistic. In any case, the main parts of the system would be a very powerful laser or microwave transmitter, which would probably be in space, a giant lens that would focus the radiation into a very narrow beam even from a long way away, and the interstellar sail itself, which could be able to catch the radiation and speed up a lot because of the pressure it created. And by sail, we do not mean a racing spinnaker, but something more like anything at least 6 kilometers in diameter and just 30 grams in weight. Accelerated to 0.2 constant in only 2 weeks, Star-Wisp might reach the Alpha Centauri system within 21 years. Antimatter propulsion is another conceivable method. We know that when 1 gram of antimatter is turned into energy, it produces an enormous amount, around 70 times the energy produced by nuclear fusion and 4 billion times the energy produced by burning oil. Such an engine would enable us to reach approximately 40% of the speed of light, reducing the time required to reach Alpha Centauri to less than a decade. However, antimatter is currently scarce in nature and difficult to capture. Therefore, it is necessary to manufacture it, which is carried out in minuscule amounts in huge particle accelerators. Making engines for space exploration would take many kilos of it, however. This appears to be a negligible amount, yet it is significantly higher than what has been synthesized to date. Consider that it would take 1 billion years for an accelerator's antimatter factory to manufacture a single gram of antimatter. The conventional energy necessary to manufacture a few kilos of antiprotons every year corresponds to a total energy consumption of around 50 billion watts, which is equivalent to the power output of all nuclear power facilities in the United States. Currently, this is our scenario. We wish to visit the planet Proxima b, but we do not yet know how. Our technology is essentially still in its infancy, despite its tremendous development. No one can foresee what the human race will be able to accomplish by the fatal year 2069, but if growth continues at the current rate, along with many new issues to be solved, we will have vastly improved our abilities in precisely those fields essential to interstellar travel. Initially, expeditions to the stars will likely be done by intelligent robotic probes, capable of moving at 0.1 constant and shrunk beyond current imaginable limitations. As proposed by physicist Frank J. Tipler and described in Arthur C. Clarke's engrossing novel The Songs of the Far Earth, even with simple probes such as these, humans could rapidly propagate throughout the galaxy. As a result of the extraordinary progress being made in the fields of biotechnology, genetic and molecular engineering, embryonic development, and cell physiology. In practice, this would involve a creation of so-called von Neumann probes, i.e., intelligent automatons that, upon arrival at their destination, would be able to construct copies of themselves and habitats for eventual living beings, including humans, synthesized in situ from the genetic code and instructions for the generation and development of embryos. After initiating the successful colonization of a planet, von Neumann's probes might construct new interstellar spaceships and automatons that would go to other star systems to repeat the feat. Obviously, we are discussing little probes and seemingly science fiction at that, but NASA will have to take into account the fact that interstellar flight with humans on board will involve mass and energy scales thousands to millions of times larger. Current understanding leads us back to the concept of interstellar arcs, which are massive, environmentally self-sustaining dwellings capable of traversing the stars for thousands of years, while numerous generations of humans, animals, and plants follow within them. These arcs might be modeled after the massive space colonies studied by physicist Gerald O'Neill in the 1970s and launched into interstellar space at speeds as low as 0.01 constant. It is impossible to conceive of the circumstances and motivations under which humans might embark on a voyage knowing that they would never reach their target. Probably only the gradually uninhabitability of our planet and other inhabited solar system planets might motivate people to make such an extreme choice. If it were possible to considerably lengthen human life, or slow down metabolic processes during flight, and achieve at least 0.1 to 0.3 constants with the requisite big spaceships, the conversation would alter drastically. For this to become a reality, however, it will take several more centuries, unless physics continues to surprise us in extraordinary ways. How then will NASA fulfill its obligations? Could it have a card up its sleeve? We simply have to wait till 2069 to find out. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we'll see you next time.